Hey guys, welcome to this super awkward video. Sorry about the angle. I had originally intended to be able to do this on my Surface Pro with my stylus, but I couldn't figure out how to record audio and draw on something at the same time without having to buy or download some new program. I thought you could do it in PowerPoint, but anyway, apparently not. So if anybody knows how to do that, let me know and I can make more of these videos, but this is how we're gonna do this today. So this is an example of recombination mapping from problem set number 2. It's A16, and it's gonna be pretty much your standard recombination mapping problem. So anytime you have to do something like this, the same strategy applies. So it's asking us to construct a map based on these mutants, and basically if there's a plus, then they can recombine and produce supposedly some sort of, I don't know, wild type phenotype. Yeah, that's what it says, produce wild type recombinants. Great. And if there's a 0, then it can't do that. So we're going to start by making a chart of everything that our mutants cannot recombine with. Okay, so I'm going to write no recombination here, and then we're just going to list the mutants. Okay. So now we're pretty much just going to go through our list of mutants, and we're going to look over here on our data and pretty much just see what other mutants each mutant just doesn't jive with. So let's start with number 1. Looks like number 1 takes issue with 8, 7, and 5. And also with itself, but that's something you can kind of ignore for the sake of solving the problem, since they should all have a 0 here. Hopefully that makes sense. If it doesn't, you can ask me about it. Okay, so we're just going to list them on the side. 5, 7, and 8. And we're just going to go down our list and do the same exact thing for all of them. Two is 3 and 8. 3 is 2, 7, and 8. So you're really just looking for zeros here, because remember, it's a chart of no recombination. 4 is 5 and 9. And essentially what this will tell you is, when you're building your map, is what is going to be overlapping with what. So if two things cannot recombine to produce a wild type phenotype, then, or genotype, I guess, then they must have some sort of overlapping mutation. Okay, so 5 is, yeah, wow, 5. Let's see. So 5 takes issue with a lot of these guys. That's going to be important for when you're actually doing your maps. So make note of that. 1, 4, 6, 7, 8, 10. So for the sake of time, hopefully you guys have kind of gotten the hang of what I'm doing here, which is really just going down each one, each mutant. So like I did for number 1, I went down here. As you get further along, you're going to have to look both at the columns and the rows to complete your chart, but pretty much that's the strategy. You make a chart like this, and it's just going to make it a lot easier for you to do a map. So I'm just going to go ahead and fill the rest of this in. So now we have our chart, and we're going to use this to build a map. So I'm going to start just by drawing a line. It's pretty much what I do whenever I'm trying to diagram a gene, map something, whatever. You just draw a line. That's your DNA. So I'm going to start with these guys because they actually give me a lot of information. In particular, what they tell me is that they are probably some sort of large deletions, right? Because they really have a hard time recombining with a lot of the other mutants here. So they're going to have a pretty big impact. So those are going to be our large deletions. And we may have other deletions. Let's focus on the really obvious ones first. And I'm going to start with those. So I'm going to go ahead and just maybe even kind of arbitrarily place 5 down here like this. I draw lines for large deletions and points for point mutants. So we have 5 here, and then we're going to go through and look at everything that 5 has an issue with. So let's start with 6. You can really start anywhere. This is kind of the part where you're going to be made to think. But you just kind of want to like start with something and then go through and just say, okay, so it has a problem with 6. Let's look at 6. It has a problem with 5. So we'll just plop it down there. We've done that. And then we can kind of look at 6 now and say, well, 6 also has an issue with 8. And as it turns out, 8 is our other large deletion. So I'm actually just going to draw that now like that. Just kind of overlapping both 5 and 6. So looks like we've solved 6, at least for now. We can go back and change anything, you know, use a pencil so that if you map something and it doesn't work when you go back to check, you can just erase it and try again. It's really at this point just puzzling through it. So 8, we've covered 5 and 6. And for 5, we've covered 6 and 8. Okay. So now we can start looking at some other things. So let's look at 1. So it has an issue with both 8 and 5. So let's put that one down and just make sure it's overlapping both 8 and 5. So I'm just going to draw it as a point here. So that takes care of 1. And then I go back up to 1 now that I've mapped it, and I see if I've taken care of all of my problems. So I had a problem with 5 and 8. 7 is somewhere in there too. So let's look at 7, see what 7 has an issue with. 7 has an issue with 1, which we've mapped. It has an issue with 3, which we haven't mapped. 5 and 8, which we have mapped. So I'm going to go ahead and say that 7 is also going to be a deletion because it's kind of also has a problem with a lot of other mutants. And it needs to overlap pretty much everything that we've written down here in order to make sense with the data. So I'm going to draw 7 as a deletion. I'm going to put it here. Let me just make sure it's not overlapping with anything it shouldn't be. So 7 overlaps with 8, 5, and 1. If we go back and check, 8, 5, and 1, that takes care of that. And so we're left with 3. Gotten that taken care of. I'm going to go ahead and just cross these off to make our lives easier. So now I'm kind of looking at 3 and wondering what's going on with that. But I haven't mapped 2 yet, so I'm actually going to take a step back and try something else. I'm going to look at, let's look at 2. Let's look at 2. No, because that, let's see, 2, 3. So as you can see, there's quite a bit of like going back and forth and planning with these. Why don't we pick something that doesn't look very problematic? Let's pick 9. So 9 just has an issue with 4 and nothing else. So there's a big mess of stuff going on down here, but looks like 9 isn't really affected by it. So I'm just going to map 9 as a point at the very end here where we don't have anything going on. Then I'm going to see it has an issue with 4. So also we haven't mapped 4 yet. So let's look at 4. So 4 is an issue with 9, which we knew, but now we know it also has an issue with 5, so that helps us map it, because we know it has to overlap with both 9 and 5. So I'm actually going to go ahead and draw that as a deletion as well. 4, so a deletion that overlaps 9 and 5. Okay. So we've got 9, 4. Great. Figured out 4. So it looks like we're almost done figuring out everything that's in 5. So that just leaves 10. So 10 is going to be somewhere in here. And that's pretty easy because it doesn't look like 10 has an issue with 9 or 4 or anything that's to the right of it. So it's just going to overlap with 5 like that. So that one was easy too. So what do we have left that we haven't mapped? We've got 6. Looks like we've still got 2 and 3 to figure out. We finished with 5, so that's done. So let's figure out maybe where 2 is. So 2 has an issue with 3 and 8. So 2 is going to go... Hey, Callie, I'm recording a video of an example for the class. So 2 is going to go... 2 is going to go somewhere where it's going to overlap with 3 and 8. Again, we don't know where 3 is, but we know where 8 is. And we know that 2 isn't having an issue with 7, so it's probably going to be all the way down here. And that just leaves, so we've got that figured out. Where's 8? We've got that figured out. That really just leaves us with 3 to figure out. So we'll look at 3 here and see it has an issue with 2, 7, and 8. And I keep saying has an issue with. Of course, that is not a reflection of actually biologically what's happening. Really, when I say this has an issue with that, it just means it cannot recombine to produce wild-type recombinants. I just wanted to make sure my lazy way of talking about this wasn't going to confuse anybody. So we have 2 here. 3 overlaps of 2, 7, and 8. So we're going to have to draw 3 as another deletion so that it can overlap with all of these. And I'm just going to draw it like this. And that should have covered it. So we've got 2, 7, and 8. Good, 2, 3. And I'm just going to take a second to make sure I have the right answers here. And that looks good. So your map doesn't have to look like this, but it should at least reflect the same logic of the same logic of kind of how this was constructed, where you take from your chart and you just make sure that if you have something that's overlapping with something else, that that's reflected in your map. So it really is just a puzzle once you get all your data organized well, I think. I think that makes it easier. So we have our map. Let's move on to kind of the second part of this. So now we're talking about complementation, and it's really important that you remember that complementation is different than recombination. So complementation is different in that it deals with genes. So you can have recombination in the same gene, and that will affect the function of the gene, and that's, I guess, usually what we're talking about. But in this case, we're talking about different genes. And so if 4 and 7 can complement, then 4 and 7 must be in different genes, is essentially how this works. So the question is really just asking you what you can assume pretty assuredly based on what they are telling you about 4 and 7. So if we look back up at our map, actually, it's saying that 4 and 7 essentially are in different genes. So we can draw some kind of a line here. And from that point on, the problem is pretty easy, and at least in the problem set. And if you see anything like this on a test or a homework problem, we're not going to necessarily expect you to resolve what's going on around here, since that's quite ambiguous, but there are some definites. So the question is asking what other pairs should definitely complement. And for example, you know that 4 and 1 will definitely complement. You know that 4 and 2 will definitely complement, 4 and 3. You can't really be sure about 8 because it's so big. And then you can go to 9 and say 9 and 2, 9 and 3. So things like that will almost assuredly complement if 4 and 7 complement. And then it will ask you what will definitely not complement, and that's just the opposite. Anything that's obviously overlapping, like, what's a good example? 5 and 6 probably won't complement. 1 and 2 probably won't complement. 2 and 3, stuff like that. So there are going to be a lot more of these than there are for things that do definitely complement. Anyway, so that's just an example dealing with recombination mapping and complementation from the problem set. Hopefully that was clear and helps, and good luck on your exams.